chapter 11 is recommendation systems. And chapter 12, we will do some kind of practice, especially on exam questions, and also introduction to the exam questions, and also show you some previous year's exam questions. So now in week 12, so I'll use the first 2 hours to introduce recommendation systems, and the last hour to show you some previous year's exam questions. And then I will use the last assignment to ask you to do the practice, show you know how the exam questions are like, and you know how to answer them in your final exam. So today we have, it's chapter 8, not chapter 7, made a mistake. And the first 6, from chapter 2 to chapter 6, we mainly learn MapReduce and Spark. The 2 big data processing platforms are the most widely used platforms for dealing with big data in nowadays. And from this week, we will learn some big data applications. And we can utilize the 2 platforms to do these applications. And sorry, still coughing. Today's topic is streaming data. We will introduce 4 problems on mining data streams. So the difference between data stream mining and traditional data processing is that in such problems, we do not know the entire data set in advance, and the data is not static, it is dynamic. Data is keep generating, and what you need to do is to do some kind of analytics over the streaming data, the dynamic data, instead of the static data. So for example, in Google, so every day we are submitting our queries to Google, right? So in Google, actually, it accepts a lot of queries. These queries form the streaming query data set. And in Twitter or Facebook, well, the users keep generating the tweets or status in the systems. So these data are also kind of a stream. And we can think of the data as infinite and non-stationary. Infinite means that your system is always receiving some data. And non-stationary means that the distribution changes over time. It's not distributed uniformly. And sometimes maybe you receive a lot of data, but sometimes the data amount is not that large. In traditional database management systems, well, data is stored in finite, persistent data sets. So you can remember the relational database, right? What are given to you is some data that can be formatted as schemas, as tables. And then this data will not be changed. So you can use tables to store the data and to query the data using SQL language. So that's in traditional database management systems. But for data streams applications, well, the data is very different. So normally the data is distributed. You have many sources to receive the data streams. So think about Twitter. So each user can be treated as one data source. So every tweet user is generating some streaming data. And data is continuous. And the data is, your system keeps receiving such data. And it's unbounded. And most of the applications, the data is being generated in a very rapid manner. And also contains a lot of noises. So it's hard to describe the data streams, but we can summarize the characteristics of the data streams as the following 4 characteristics. The first one is there's huge volumes of continuous data, possibly infinite. And it's fast changing and requires fast real-time response. So for dealing with streaming data, normally we we expect to have some real-time processing to get the results for the queries instantly. And the random access is always not possible. It's very expensive. And because the data is generated, is received in the data generation speed is very fast, and also the data volume is very huge. It's not possible to store all the data in some place. So it's different from the traditional database where you can do random access, such as in tables. Okay, we can go to some rows and to retrieve the data. But in streaming data, normally you can only scan the data once. And so you can only keep some kind of statistics of the data instead of the whole data stream. And we can only store some kind of summary or some statistics seen so far. It depends on what kind of applications we are trying to deal with. And so different kind of summaries you can keep for the processing. Here are some examples of the data stream applications. So for example, there are 3 billion telephone calls in US each day, and 30 billion emails daily, and 1 billion short messages. And you can also see some statistics in Twitter, in Facebook. You can see how many tweets will be generated every day. It's a huge number. And in the scientific area, so NASA's observation satellites generate billions of readings every day. And for network, the IP network traffic is up to 1 billion packets per hour per router. So each ISP has many routers. You can imagine how large data streams the ISP need to deal with. So in data stream applications, so the input elements enter at a very rapid rate at one or more input ports. So normally there will be many sources. So as I said, so you can think about Twitter. So each user can be viewed as input port, one data source. And we call the elements of the stream tuples. The system normally is not able to store the entire stream for random access. So the question is, how can we make critical calculations about the stream using a limited amount of memory or disk? So we only have limited computing resources on each computer, right? So, but the data stream is infinite. So how can we utilize limited computing resources to do the data stream applications? So that's a main question. So this is a system about traditional database management system, the architecture. And so the processor will receive the queries and also communicate with the data storage, such as RDBMS. And in big data area, we also have some other big data processing platforms. And these are used to store the static data. Okay, so the processor receives the queries, and then to communicate with the data storage to retrieve the answers for these queries, and then generate the output, send output to the users. So that's the architecture for DBMS. But in DSMS, data stream management system, so architecture is totally different. The major difference is that the data is not static, right? Here, well, the data is already given to you. Okay, so sometimes it may be updated, but update is not frequent. So you can do the update offline. But here, the data keeps coming to your system, to the DSMS system. And there are also many data sources. So for the processor, okay, he needs to receive queries, but also he needs to receive the streaming data. So if you still remember Spark streaming, when I showed the example to you, you need at least 2 threads, one thread for receiving the streaming data and another thread for dealing with query processing. So that's just about this architecture. So you always need to receive the data streams and also have some computation resources for dealing for processing queries. And another difference is that because data stream is the volume is very huge, and normally we are not able to do the random access, and we are not able to use the entire data set the data we have received so far for query processing. And normally in DSMS, we will use a limited working storage, such as limited memory and limited disk, to store some summary of the data streams you have received. And the whole data set, also, this is optional. The entire data streams may be stored in some other storage for archive. And the query processing is mainly based on this part, based on the limited working storage, not on the entire data streams. So the results are always approximate, not the accurate exact results. And based on the limited working storage, so we store some summary of the data streams, and then based on this summary, for the queries we received, we do some processing and send output to the user. So that's for this DSMS architecture. It's different from the DBMS system. And so in relational database, okay, so you receive the queries and you use SQL language to do query processing, and your main memory is used to cache some data read from disk. And on disk, your data is stored as table, the schemas, and the result is sent to the users. But here in DSMS, because the data is dynamic and your query is always a continuous query, it means that given this query, the results keep changing. You need to update the results to the user. Because when some new data streams comes to the system, and the result to this query actually is changed, so you need to update this change to the querying user. So that's how it is called continuous query. Here, the query, you only need to process it once. The result is, so if you submit this query to the system, okay, your answer is fixed. It's just like that. And you can just process the query and send the result to the user. But here, because data is not static, it's dynamic. And as a result, the result of this query keeps changing. So your system needs to update the changes of the result to the current user. And also, your system needs to receive the data streams. And compare the two architecture, DBMS and DSMS. In DBMS, well, we store the sets of relatively static records with no predefined notion of time. And it's good for applications that require persistent data storage and complex querying. So you can do a lot of complex queries, such as in SQL language, you can do a lot of queries, right? And in DSMS, it supports online analysis of rapidly changing data streams. So the data is very different. One static, another one changing dynamic data. And for data stream, it's real time and continuous. And normally it's too large to store entirely. And we can only store the summary of the entire data streams we have received so far. And there's no ending. And the queries is also continuous. You need to update the result changes to the current user. And so there's a more detailed comparison between DBMS and DSMS. So for data, and here is in DBMS, it's a persistent relations. And your schemas are fixed. And your data, after you can have some update, but this update can only be stored in these schemas. And for queries, it's only one time. But here in DSMS, it's continuous queries. It's not one-time query. And in DBMS, you can do random access. So you can go to the tables and to retrieve any row of the table. But in DSMS, it's not possible to do the random access because the cost is very expensive. So what we can do is only a sequential access. So the data is received and streamed in the system. So your system is only able to scan the data stream once and store some summary for later query processing. And in DBMS, so you can assume that you have very huge disk store for storing the data. But in DSMS, we only have bounded main memory for query processing. We use main memory because in DSMS, normally we trying to do real-time query processing. So using memory is able to satisfy the real-time requirements. But if you do queries over disk, then the query processing time will be very long. And the memory number is bounded, so we are not able to do the entire data stream scan. So we can only store the summary. And some other differences, such as in DBMS, and the update frequency is very low, but in DSMS, the data keeps changing all the time. And so in DBMS, we always assume precise data, and the result is always accurate, exact. But in DSMS, because we are not able to store the entire data set, we use a summary to process queries. So the results is also imprecise and have some it's approximate. Okay. So today we will learn 4 topics on data stream mining. The first one is about sampling data from a stream. So the reason is because the original data stream is very huge, and we are not able to store such huge stream. And instead, we wish to store a sample of the data stream, and this sample can reflect the distribution of the original data set. And so we can, based on the sample, we can do some query processing, such as some distribution relevant queries. And the second topic is queries over sliding window. And to do the problem we are trying to solve today is to count the number of items in sliding window in some time period for the elements you received within this time window. And the third topic is filtering data stream. The problem is to select elements with property X from the stream. So given requirements, so what we want to do is we want to select, we are given some property, and we want to select these the elements with such property from the large data stream. And the last one is to do the count distinct elements. And this to count the number of distinct elements in the last k elements of the data stream. So we will see how we can solve these problems in the data stream setting. And it is very different from the static data setting. And so the algorithms are also very different. For data stream mining, it has a lot of applications. So previously, we see some examples of the big data streams. And here are some examples of how the big data streams can be utilized in big data problems. So first one is mining query streams. So in Google, Google wants to know what queries are more frequent today than yesterday. So Google Trends, right? So if you know what is Google Trends, you can compare. And so based on the huge streaming queries, so you can do this based on some summaries of the query streams instead of the whole entire query stream. And mining click streams, so it's from Yahoo. Yahoo wants to know which of its pages are getting an unusual number of hits in the past hour. The kind of anomaly detection, also based on data streams. And this is for the applications in Twitter and Facebook. So it's also about check the social network news feeds for looking for trending topics. And in sensor networks, different sensors keeps generate some readings. It's also the data stream data sources actually. And based on the sensor readings, we can also do some a lot of tasks and telephone call records. And IP networks. So based on the data streams, and there are a lot of problems you can deal with. Here's one example about in IP network data. The network's sources of massive data, the data per hour per IP router is of level gigabytes. So the fundamental problem of data stream analysis in this IP network application is that it's too much information to store or transmit because data streams, the volume of the data stream is too huge, and the speed of the data generating is also very rapid. And so process the data, in order to process the data, we can only do one pass scan, sequential scan, and use very limited space to store the data summary. And based on this, we can provide approximate answers to the question. Normally, these approximate answers have performance guarantees based on the probability theories. Okay, so let's move to the first topic. Is about sampling data streams. And as a side, because normally we are not able to store the entire data streams. And one method to solve this problem is to store the sample instead of store the entire stream. But sample can reflect a random distribution. So for example, the random data stream is like this. We have different dots with different colors: red, green, yellow, blue. And after the sampling, so we have much smaller data. But this data can reflect the original data distribution: red, green, yellow, blue. It's just roughly the same, not exactly the same. And to do sampling, there are two different ways. And the first is very straightforward and very easy. It's to sample fixed proportion of elements in the stream. For example, so given the whole stream, we only want to store 10% of the whole data stream. And the problem is that as the stream grows, the size of the sample also gets bigger, right? So after you receive the data streams for a long time period, and your sample size also increase, and maybe it's too huge to store in your computers. So therefore, in order to deal with this size volume problem, we can use another approach to maintain random sample of fixed size over potentially infinite stream. So the difference here is the size is not fixed, but the proportion is fixed. Here, the proportion is not fixed. The size is fixed. The sample size is always like this, such as 100 megabytes or 1 gigabyte. So we always use this such space to store the sample for the data stream. And because the data stream keeps increasing, right? So it means that it's not able to guarantee the proportion. The original distribution cannot be guaranteed, but we can have some kind of performance guarantee based on the probabilistic theories. And the sample of the fixed size, because the sample is the size of the sample is fixed, so it's not affected by the data stream volume. And at any time t, we would like the random sample of S elements to satisfy some requirements. So what is the property of the sample we want to maintain? Because we are not able to maintain a original distribution. So what kind of other properties that the sample can maintain? So that's a key question. And so for all timestamp t, each of t elements seen so far has equal probability of being sampled. So we will see more details about this sentence because it's not easy to understand this sentence here. We will see more details. And that's the property that we want to maintain to guarantee some kind of probabilities for the sampling. Let's start from the easy problem to sample fixed proportion. And for example, in search engine, we have query streams, and we have a stream of tuples, user and query, and the time for submitting the query. So that's one tuple, and the tuple keeps coming to your system. Okay, and the answer, your problem is to answer the questions such as how often did the user run the same query in a single day. So if to do the fixed proportion sampling, so we can do such as we can store the 10% of the query stream. Okay, one naive solution is that okay, we generate a random integer in in the range 0 to 9 for each query. And then we store the query if the integer is 0. Otherwise, we discard. Okay, so that's by using this way, we can keep a sample of 10% of the original data stream. And so this is very easy, right? So we just use a random integer to do this task. But think about this question, another question. So what fraction of queries by an average search engine user are duplicates? So assume that we have a user, okay? Each user issues X queries once and D queries twice. So in this system, we have X plus D distinct queries, right? But 2D queries are duplicates. So in total, the number of distinct queries is X plus D, and total number of queries is X plus 2D, because that's a problem. And based on this setting, in order to compute the fraction of queries each search engine user are duplicates, so we can do the computation like this, right? So D queries are duplicates, and the number of total distinct queries is X plus D. So for answering this question, so it is X divided by X plus D, right? So that's very easy. But if you do sampling, think about if you do sampling, we still just store 10% of the original queries. How the result will be like? We just keep 10% of queries. Okay, and this sample will contain 10% of X, right, of the singleton queries, and and 10% of the first D queries, and 10% of the second D queries. Right, so in total, it's 20% of D queries. But based on this sampling, if we remember that we are using the sample data to do the computation, okay? So in the sample data, we have 10% of X queries that are distinct, okay? So that's one part of distinct queries. But remember that now the 2D queries, we only keep 10% of them. So the duplicate is not the same as original 2D queries. In the original 2D queries, so we have 2D queries, and each query appears twice, and all these D queries are duplicates, right? But remember that now we only keep 10% of the 2D queries. So some queries are duplicate, but some D queries actually are not duplicate because only one copy is sampled. Another copy is not sampled, right? So in order to do the computation, we need to count the number of distinct queries and number of duplicate queries based on the sampling data. Okay, so this part, 10% of X queries, okay, they are distinct. And for duplicate queries, only these pairs are duplicates. So you get 10% of the first copy of the queries and 10% of another copy of the queries. So for the probability of duplicate pairs is this value. And of all the duplicate queries, this proportion appear exactly only once. The computation is because of this. So 10% probability of the first copy is being sampled, but 90% of probability it is not sampled. The second copy is not sampled. And another way is that, okay, so the first copy is not sampled in probability of 90%, and the second copy is sampled of probability 10%. So in total, the distinct, and these queries, actually, they are not duplicated in the sample data. So as a result, to do the query, to answer this question, actually, based on the sample data, you only have these queries duplicated, and these queries, the total number of distinct queries. So as a result, it's not the same as this answer, right? So all these computations are based on probabilistic expectations, and so this is the expected result. But expectation of the computation based on this sample data set is not exactly the same as this one. So it means that doing such sampling has some problems. So I'm not sure if you have understand this this part. So if you do not understand the numbers, it's fine. You do not need to. You can see the slides later. You just need to know that, okay, for keeping 10% of the D queries, and it's not like the original data set. In the original data set, all the D queries are duplicate, right? But now you sample 10% of D queries. But these 10% of D queries, some of them are duplicated, but some of them are not duplicated. So as a result, the sample data is different from the original data. So that causes problem. And to solve this problem, what we need to do is to do the sampling based on users, not based on queries. And so we can use a hash function that hashes the username or user ID uniformly into 10 buckets. So we hash each username to one of the 10 buckets from 0 to 9. And if the user hashes to bucket 0, then we accept this such query for the sample. And if not, then we just discard it. So by doing this, well, it's different from this sampling approach. This sampling approach is based on queries. We keep 10% of queries. But here, we keep 10% of the users. Okay, so that's why the two sampling solutions are different. And this can guarantee the original queries distribution. But this is not able to maintain the original query distribution. And based on this example, you should know that for the fixed proportion problem, the major problem is that how your sampling approach can maintain the original proportion, can maintain the proportion of the original data stream to maintain the original distribution of the original data stream. That's a major problem. If your sampling approach is not appropriate, you may get some problems. The answer based on your sample data will be very different from the answer based on the original data stream. Okay. So in general, this problem is like this. So given a data stream to you, and your task is to take a sample of fraction A divided by B, and the stream of tuples with keys. And key is some subset of tuples components. So for example, in the previous example, the tuple is user, search, and time. Well, in this problem, the key is a user. And the choice of the key depends on the application. So in the previous example, well, the user should be the key, and we do the sample based on the keys. To get a sample of A or B fraction of the stream, so what you need to do is to do some kind of hashing. So you hash each tuple's key uniformly into B buckets, and you pick the tuple if its hash value is at most A. So you can, by doing this, you can generate sample of fraction A or B of the original data stream. So if you want to get 30% sample of the original data, so you hash into B 10 buckets, and you take tuple if it is hashed to one of the first 3 buckets. Actually, you can select any 3 buckets to do this step. You just need to select 3 buckets from the 10 buckets and to do the sampling. Then your answer should be correct. Okay, so that's for the first solution, to keep a fixed proportion of the original data stream. This should be very straightforward and easy to understand. The only problem is that you need to select the key appropriately. For example, in the previous example about the queries, you cannot use the search query as a key. Instead, you need to use the user as a key. And based on the users to do the sampling instead of using the queries to do the sampling. So that's most important problem, important thing you need to think about when you do fixed proportion sampling. Okay, so now let's look at the second approach about fixed size sampling. Well, this is more complicated and more difficult to understand because this stream keeps increasing, right? So how can we use only fixed size sample to represent the original data stream? So that's one question. What kind of property we want this fixed size sample to maintain in order to guarantee the query performance, right? Okay, suppose that we need to maintain a random sample S of size exactly S tuples. And for example, the main memory size is constrained. So we only have S megabytes to do the sampling, okay? And we use fixed size sampling is because the stream is infinite, and we are not able to know the length of the stream in advance, and we are not able to store the entire stream. So we wish to use a fixed size sample to store the summary of the data streams we have received, and then to provide the approximate answers to the queries over the data streams we have received so far. Okay. Suppose we at time n we have seen n items. Well, each item in the sample S with equal probability S over n. So let's look at this example. How to think about the problem? Assume that S is 2. We only keep 2 tuples all the time. And the stream we received is like this. A, X, C, Y, Z, K, C, D, E, G, infinite data stream. So we want to use only 2 characters to represent the original data stream. At time 5, n equal to 5, and we received 5 elements. Okay, so each of the first 5 tuples is included in the sample S with equal probability. So the idea of the fixed size sample is to guarantee this. So at any time point, and we wish that all the tuples we have seen, we have received so far, is included in the sample size, in the sample set S with equal probability. It's based on probability, okay? And at time n7, and the sampling approach can guarantee that, okay, so we have seen 7 tuples, and these 7 tuples are stored, the 7 items are stored in the sample set S with equal probability. And that's what we want to achieve. We want to guarantee that all the elements we have seen so far are sampled, are stored in the sample set with equal probability. So that is fair for all the elements, right? So that's what we want to achieve. One practical solution is to store all the n tuples seen so far. And then out of them, we pick S at random. So this can guarantee the probability. So all of them are selected into S with equal probability. But that's impractical because we are not able to store all of them. So another thing you need to notice that the same item is treated as different tuples at different time steps. So this C and this C, they are treated differently in this problem, in this goal. Okay, so for example, we have we use n equal to 7 as 10.7 for example A, X, C, Y, Z, K, C. So in these 7 characters, so actually each item of the 7 each of the 7 items will be sampled with equal probability. Okay, so as a result, because actually C appears twice, so this C has 1 probability to be sampled, and this C has a probability to be sampled. And because there are 2 C's, and the other items only appears once, so as a result, according to this to the probability, so actually C has a larger probability to be sampled in the sample set. So that's why this fixed size sampling approach can somehow maintain a random distribution. If an item appears more frequently, so the probability of being sampled is higher than the other items. So that's why I said the items of a different time steps received treated differently, because each such item has some probability to be sampled. For solving this problem, there's the algorithm called wall sampling. The algorithm is actually very easy to understand. The process is very simple. But this algorithm can guarantee the goal we want to achieve. It can guarantee that at any time step, and all the elements we have received so far have equal probability to be sampled, to be contained in the sample data set. Okay, so let's see the algorithm. We will store all the first S elements of the stream to S, because all the first S elements can be stored in the sample set, right? So we put all of them into the sample set. And next, we will see more elements. So if we see more elements, it means that we need to use this sample set to represent the original data stream. We need to do some kind of processing to guarantee the goal we want to achieve. Suppose we have seen n-1 elements, and now the nth element arrives, okay? So n is larger than s. So we have seen more elements than the sample set size. And with probability s divided by n, we keep the nth element, and s discarded. So with this probability, we keep the new element. And if we picked this element, then we have s plus 1 element now, right? So we need to replace the old elements in S with this new element. So this element will replace one of the current S elements in the sample set S, and we picked uniformly at random. So one element from S will be selected, and it will be thrown out of S, and then we put this new element into S. So by doing this, we always keep the size of the sample as S. And this algorithm can guarantee that at any time point, all the elements that have been received by our system so far has equal probability of being sampled, of being contained in S. So the algorithm is very simple, but the key part is that why the result obtained by this algorithm can achieve this goal, right? So this algorithm maintains a sum S with a desired probability. That is, after n elements, the sample contains each element seen so far with equal probability of S over n. Why it is like this? We will do some analysis. So you can see that the algorithm is very easy. Only 2 steps. So for the first S elements, you just put them into S. And then next, for new elements, the first step is to check whether you want to keep it or discard it. And you keep it with probability S over n. And next step, if you discard it, then you do not need to do anything. But if you keep this element, so you need to do the second step. You will pick, you will select one of the S elements at random uniformly, and you throw out this element from S. Then you put this new element into S. So that's it. That's all. That's the algorithm. But why it can maintain its probability? So that's a problem we want to start in. We can prove this by induction. So we assume that after n elements, the sample contains each element seen so far is with probability S over n. So this is assumption of our induction, okay? And what we need to do is we need to show that after seeing the element n plus 1, the sample maintains this property. So the sample contains each element seen so far with probability S over n plus 1, right? So that's the induction step. It's assumption, and that's what we want to achieve. The base case is very easy, because initially we put all the first S elements into S. So all the S elements, they are selected, they are sampled of equal probability 100% S over S. So next, the inductive hypothesis is after n elements, the sample S contains each element seen so far with equal probability S or n, right? And now we get n plus 1, the new element n plus 1. The inductive step is that for each element already in S, so the probability that algorithm keeps it in S is a little bit complicated. So let's look at this equation step by step. For elements that already in S, the probability that the algorithm keeps this element in S is like this. So first, this probability is that, so you still need to think about the algorithm, okay? So the new element, if it is discarded, if the new element is discarded, so you do not do nothing, you do not need to do anything. So all the S elements are actually kept in S because they are not changed. So what is the probability of their being kept is that the new element is discarded, right? So of this probability. So go back to this algorithm, you can see that the first step is with probability S over n, we keep the new element, okay? So what is the probability of discard this element as to 1 minus this probability. So of this probability, we will discard this new element. So by this probability, okay, all the elements in S will be kept. So it will not be changed. So that's for the first situation. And for another case is that the new element is not discarded. So the probability is S over n plus 1. Of this probability, the new element is not discarded. And if it is not discarded, so we need to do the second step. We need to replace one element in S with this new element, right? So we will select one element in random uniformly from S. Okay, so this element, it is not picked, it's of this probability. If it is picked, it's of probability 1 over S, right? So if it is not picked, it's of this probability. So this just corresponds to the two different possibilities of the algorithm. The first part is that the new element is discarded. So if it is discarded, so all the elements in S will be kept. So that's for the first case. And this is the second case. For the second case, the new element is not discarded. It is not discarded, and then element in S, it is not sampled. It's not picked out of this probability. So you do a multiplication of the two probabilities. So in total, okay, so this is a entire probability of this element in S is still kept in S after this new step. So the probabilities of this n divided by n plus 1. So by this probability, the element already in S is still kept in S after the new element arrives. Okay? And so at time n, the tuples in S were there with probability S or n. And so at time stamp n to n plus 1, well, the tuple stayed in S with probability n divided by n plus 1. So therefore, the probability of the tuple is in S at time n plus 1 is of this value, S divided by n here, multiplied by n divided by n plus 1 here. So the probability is this. So this probability is that this element we have received so far has the probability of this element being sampled. Okay. So this is exactly the same as what we want to achieve in this slide. That's what we want to prove. Okay. So the algorithm is very simple. And the difficult part is that how to understand why it is correct, why this algorithm can generate the sample set that can maintain this property, that is, by any time point n, all the elements we have received is sampled of equal probability as the sample size divided by n, the number of the elements we have received so far. And so that's a conclusion of this algorithm. So in order to prove that, so we use induction to prove this. And the major step is here. So we assume that this is our induction assumption. We assume that after elements, the sample set S contains each element seen so far with probability S over n. What we want to achieve is that we want to prove after n plus 1 elements received, and the sample set S still contains each element seen so far with equal probability, but the probability value is S divided by n plus 1. That's what we want to prove. And this is proof details. So this is inductive step. This is a probability n divided by n plus 1 is a probability that the element already in S being kept in S. And so in order to show the final probability, we also need to get another probability, which is the tuples in S attempt n, the tuples in S were there. This probability is S over n. So we do a multiplication. This is a probability of each sample seen so far being sampled, being picked up in S. So that's our final conclusion. If you still have difficulties of understanding this proof, you can go to the textbook. You can read the textbook. The book should have more details to help you to understand. Okay, and the most important thing here is that you remember the steps of the algorithm, how the algorithm works. You know how to apply the algorithm to a data stream to get the correct sample. Okay, so that's for the first topic. Then we move to the next topic after a short break.
large sample file you have given, two or three places I'm getting a different node values. Like instead of 0 in the last case, it is having 6 in my case. So rest of them are same.
I think that's not a big problem. So at the sites, according to notice, you will not lose marks because of precision problem. So if it is just a precision problem, that will be fine. Yeah. But the tutors will check if the results are different. And tutors will check the code to see if the logic of the code is correct. So you will get most of the marks if your code is okay.
Okay, because in my case I tried to debug it to find what is the problem. The value is 3,560 in your case, and in my case it was 66.
Okay, I don't know. I'm not sure what is the problem, but no worry. I think I'm going to get most of the marks.
Okay, I was suspecting that there might be a conflict, like same value. So my node is selecting 66 in my case, and
maybe that is possible. That is possible. Yeah, that's possible because there may have multiple passes with the same distance. Yeah. Okay, so don't worry about that. Yeah.
Thank you.
Okay. Okay, let's go to the move to the next topic. It's called currying data streams. And the first topic is to do sampling. The objective is to maintain a sample that can reflect the original, the distribution or some property of the original data stream. And the second topic is to do the querying, to query over the data stream within a sliding window. The problem is like this. Okay, so so first let's look at what is a sliding window. What does a sliding window mean? Useful model of stream processing is that it carries about a window of less n, the n most recent elements received. And if you remember when we learned Spark streaming also provides a sliding window. I also provide you the sliding window for you to use. And when you create a Spark streaming context object, you can specify the size of sliding window. Here it's just exactly the same like as that. So you are given a window size, and this window size tells that you only need to focus on the most recent elements. And all the query processing are based on the most recent elements you received. But one problem is that n may still be very large, and as a result, you cannot store all the n elements in memory or even on disk. So in order to do the query processing over the n elements, well, you need to do some kind of processing to store the summary of these n elements instead of the original n data elements. And in Amazon, so the example is like this. So for every product X, we keep a stream of values 0 and or 1 to indicate whether that product was sold in the nth transaction. Okay. So if we want to answer queries, how many times have we sold X in the last K sales? So that's such a query. How such a query can be used in real scenarios. So this is one example about the sliding window on a stream. Okay, so assume that we have sliding window of 7, and this is a current window. So this is the past data. This is the future data. Okay, it means that we are at time here. We are at time point here, and the most recent 7 items we receive is from S to K. And next, we move forward to the next time step. We receive one more element. So the window is moving here. So actually the data is moving in this direction, and the window is not changed. But because now we are not able to show the data moving, so actually in this slide we show the window moves to this direction. So similarly, Next timestamp, the window keeps moving to the next element, and to the next element. And the queries over sliding window is that you always do query processing over the data streams within this window size based on your current timestamp. Okay, so the problem here is that given you a stream of 0 and 1s, and your task is to answer queries of this form. So how many 1s are in the last k bits within the most n recent elements? So k is smaller than n. And one naive solution is that you just store all the most recent n bits. Okay, so each bit represents whether element is so as in the Amazon example, so each bit represents whether this product has been sold out within the nth transaction. And so the simple solution is that you store all the most recent n bits. And when a new bit comes, you just discard the n plus 1 bit and store the new coming bit. Okay, and based on this these n bits, you do a count all the number of to count all the ones and return the number. But as I said before, as shown in the previous slides, normally it's not able to store the n bits because n may be very huge. It may be very large. And you're not able to store all the n bits in memory. So as a result, you need to store some kind of summary of the most recent bits. But because it is just a summary, it's not exact data, right? So you are not able to get an exact answer without storing the entire to store the elements within the entire window. The real problem is that what if we can't afford to store n bits, but we can still guarantee some performance? Okay? So if n is 1 billion, so normally you are not able to store 1 billion bits in memory. So you need to store something else that can reflect some properties of these 1 bits elements. And based on this summary, we do the query processing. Okay. And most of our data stream applications, we are happy to have approximate answers instead of exact answers. Because first thing is because it's not able to get exact answers. And second is because most of the time, approximate answer is very close to the exact answers. And so they are acceptable to most applications. This one attempt still one very simple solution. So remember now, we are not going to store all the n bits, but store some kind of summary information of these n bits. But this summary information can still be used to answer the problem. So to answer the question. The question is that how many ones are within the most within the k bits within the most recent bits. Okay. And how many ones are in the last n bits? Let's look at this question. One simple solution is actually does not really solve our problem, but we can just start from a simple solution to get some ideas, to get some intuitions. And we can maintain two counters. One counter is S, the number of ones from the beginning of the stream. And another counter is Z, is the number of zeros from the beginning of the stream. Okay. And how many ones are in the last n bits? We can just use this one to do an estimation. S is a number of ones from the beginning of the stream, right? And Z is a number of zeros from the beginning of the stream. So if we do not store the n bits, but we still want to have a guess of how many ones are in the last n bits, so we can utilize historical distribution of 0 and 1s to predict the number of ones, right? That's n divided multiplied by the proportion of ones. So that's just one guess. But the assumption is that the 0 and 1s should be distributed uniformly. But if it does not distribute uniformly, then this guess actually is not it's not accurate and has no performance guarantees, right? So as the distribution changes over time, then this answer obviously is not correct. Okay, and because of this, so these four authors, they propose the DGIM algorithm to maintain the stream statistics over sliding windows. This paper is published in SODA in 2002. So SODA, we call this conference SODA. SODA is a very famous conference in computer theories. And so this is a well-designed algorithm. And this algorithm, it does not assume uniformity. So the data is not uniformly distributed across the data stream. And the space cost of this algorithm is very, very small. We only need to store this log n times log n bits per data stream to answer the queries approximately, to answer the number of ones approximately. So normally log n is very small, right? So log n multiplied times log n is also very small. It's the space cost is very excellent. And this solution gives approximate answer, never off by more than 50%. So you can see there is a performance bond, there's a performance guarantee. So your error will never be more than 50%. So in fact, in this algorithm, the error factor can be reduced to any fraction. It's more complicated algorithm and more space cost. So this is a summary of this algorithm. Okay, so this algorithm does not assume uniformity, and it has very good space cost, and it also has a performance answer also has a performance bond, and the performance guarantee actually can be reduced to any fraction larger than 0. Let's look at the idea first. Okay, the idea is to utilize exponential windows, and okay, so we still start from relative simpler solution, which actually does not quite work in this problem, but it still shows the idea of this algorithm. It summarizes the exponentially increasing regions of the stream, so looking backward, and drop small regions if they begin at the same point as a larger region. So for example, we have this data stream. We have a data stream of 0, 1, 0, 1, 0, 1. And so this is the size of n we care about. Okay, so we are trying to count the number of ones within this n bits. And what you do is to use these regions, and the size of the regions increases exponentially. So for example, it is 1 bit, and there's 2-bit regions, and 4-bit regions, and there's 8-bit regions, and 6-bit regions. And within each region, we count the number of ones in this region. So for example, here it's 0 ones, 1, 1. And here in this region, only 1. And in this region, 2. This region, 2. This region has 3 ones. This region has 4 ones. Okay. And so that's, remember that what we store, okay, so we do not store this data stream. We store the regions together with their starting point and their number of ones. So that's what we store. So this is a summary of the data stream. And based on these regions, see if we are able to answer the question number of ones. So, okay. Assume that if your k is to this point, okay, well, to this point, based on the information you stored, okay, you are able to give the answer because it's from here, 10 plus 2 plus 1, right? So you have 13 ones to here if your k is this part. But problem is that you are not always that lucky, right? So assume you want to know the number of ones in the n base. So n is here. So you only have the information about these 16 bits. You only know that from this bit to here, we have 6 ones in this part, right? So the problem is that you do not know the 6 ones is here or here. You have no information about that. So this causes a problem. But anyway, you still see some ideas, right? You still, if you keep some information like this, you are still able to answer the question approximately. The only problem is that we do not know where the 6 ones appear. This part or this part, we are not able to know. Okay. And for this solution, what's good? Because it stores only log n square bits. So we have all log n regions, actually. And for each region, we only have log n bits to store the number of ones. And the update is very easy. If your more bits comes, you just need to update the regions, update the number of ones as well. And the error comes here. There's an unknown error. So for that part, you have some error. But if it's not if the bits you're trying to compute does not cover this part, well, your results still solve this problem perfectly. So what's not so good is just because here is this problem. As long as the ones are fairly evenly distributed, the error due to this unknown region is small. It's no more than 50% because it's evenly distributed. But it could be that all the ones are in the unknown area at the end, right? So because of this, the error actually is unbounded because here all the ones are in the unknown area, but you treat these 6 ones to included in your answer. So let's call this this problem. The error is not bounded, and so you see this problem. You see some idea of this this algorithm is to use exponentially increased buckets or regions to store some information, and this information can be used to answer the question approximately. Okay, but what caused the error here is that you are not able to know the number of ones is for which part. It's for unknown error. If you include the 6 ones into your answer, but actually they are all in the unknown error, well, the error is very large and the error is not bounded. In order to overcome this problem, well, let's look at the real DGM algorithm. So instead of summarizing the fixed length blocks, and we do the summarization of blocks with specific number of ones. Okay, so in the previous in this solution, the region corresponds to the bits, the number of bits. So we start from here and 1-bit region, 2-bit region, and 4-bit region, 8-bit region. But in the improved version, in the fix-up, in the real DGM algorithm, we are not storing the region like that. We are storing the blocks with specific number of ones. So let's block sizes increase exponentially. So we store 1 block. Okay, this block contains only 1 one. And the next block contains 2 ones. And another block contains 4 ones. But this block, even they have the same number of ones, but their covering bits may be different. Okay. And if there are few ones in the window, so the block sizes stay small. So the errors are small as well. So as shown in this example, what we do is like this. So this is 1 block with only 1. It's the next block with only 1. And this block with 2 ones. And this block with 4 ones, block with 4 ones. So you can see difference from the previous solution. The previous solution, you use exponentially increasing regions, and that each region corresponds to some bits. But here, each block corresponds to some bits containing some number of ones. So that's a difference. And this block contains 8 ones. So actually, this block and this block, they contain the same number of ones, but actually the bits they covered is different. Sorry.
In this graph, why do you only have the yellow block, these two ones, like for once, but for all other blocks you have them for twice?
I will show more details about algorithm in later slides. This is just one step within the algorithm. So in some steps, it depends on your data streams. And it just means that in some intermediate steps, for some data stream, and your block may be like this. Okay. But at most, for each for each size of for each number of ones, you only have at most 2 blocks for that number of ones. Okay, so that's a basic idea of this algorithm. Well, now in this new solution, okay, so each bit in the stream has that's time step as well. Time step is also used to reduce the space cost. And because we only care about the most recent n bits, so we will record the time steps modular n, the time window size. So we can represent any relevant time step in all log n bits. So this can help to reduce the space cost of this algorithm. And the time step will be used to record the start point of each block. So for example, given the window size 40, while time step 123 will be recorded at 3. So we do not use 123 to represent this time step, but we use 3. So this can reduce to reduce the space cost significantly. Okay. Okay. So about this algorithm, as shown before, the most important structure is a block. Okay. The block contains some number of ones and also has a starting point, and this starting point is represented as a time step, and the time step is obtained by the original time step modular the window size n. And this block actually is called the bucket in this algorithm. So this bucket is a record consisting of a time step of its end. So this represents where it ends. Its starting point is also fine, but end is more it's easier to determine whether it is out of the window range. Okay, so we have one time step to record the end of this bucket, and another value is number of ones between its beginning and end. So the number of ones within this bucket, how many ones are contained. So this is log n bits about the space cost for the time step. And for the number of ones, it's log n bits. So you can think about why it is log n. Okay? And this is the most important feature of this algorithm about log n. So it's not log n times log n, it's log n. It's a very, very small value. Okay? You can think about this question and to see if we can figure out why it is like that. And this is the structure of this bucket, one time step and the number of ones. And for the constraint on buckets, so the number of ones must be a power of 2. 1, 1, 2 ones, 4 ones, 8 ones must be a power of 2 for the number of ones. And that explains the O log n in B above. Okay, so this is the hint. The number of ones must be a power of 2, and this can guarantee that you only need to use log n bits to store the number of ones. So if you cannot find out, you cannot understand why, then you can try to discuss with me. Okay. So this is still the example as shown previously. Number of it's 1 1 in this bucket and 1 1 in this bucket. Okay. So for each bucket, we have one time step to represent its end, and also the number of ones within its bucket. So the time step will be help to check if this. Sorry, here. So this is the end, and it will help to check if this bucket is out of the current window size. If it is already out of the current window, so you can discard the bucket. It's not useful anymore. And how we can represent the stream by this bucket? The algorithm is like this. And right end of the bucket is always a position with a 1. So in this example, and all the right position of each bucket is always a 1. Actually, the left position is always a position with a 1. And every position with a 1 must be in some bucket. So every 1 must be in some bucket. And either 1 or 2 buckets with the same power of 2 number of 1s. So 1 or 2, at most 2, for the same power of 2 number of 1s. And the buckets will not overlap in time steps. So all the buckets never overlap. And the buckets are sorted in by size. The earlier buckets are not smaller than later buckets. So these are earlier buckets. So remember the data, this is a past data, this is the new data. So this is the earlier buckets. The earlier buckets is always no smaller than the later buckets. And the buckets will disappear when their end time is larger than n, because now it means that this bucket is out of the window size. So it is not useful in the query processing. You can discard its bucket. In this example, you can see how the stream can be represented by buckets. So we have 2 buckets of size 1 here, and 1 bucket of size 2, number containing 2 1s, and 2 buckets of size 4 here, 2 size of bucket 8, and 1 bucket of size 16. And this bucket is partially beyond the window. It's still useful, so you cannot discard it. And 3 properties of buckets that are maintained, either 1 or 2 buckets with the same power of 2 number of 1s. So either 1 or 2, remember, at most 2. And buckets do not overlap. All the buckets never overlap. And buckets are sorted by size. So the earlier buckets are always no smaller than later buckets. And so that's summary information we need to keep for representing the data stream. And when answering the question, okay, for answering the number of 1s for within the window size n, so you can see how you can answer, okay? So just sum up all the number of 1s within each bucket. So from here, sum them all together. And for this part, it's not for sure, right? You only know that some 1s are in this part, but you do not know how many 1s are actually within the time window. And you have several solutions. You can add all the 1s into your result. You all add half of them, and so this can guarantee. Because now the bucket it's a bucket, it's not a region like the previous solution. Well, the error is bounded. It's different from the previous solution. So I will show details later. Now let's look at how to maintain this summary information, to maintain the buckets when your data stream is coming. When a new bit comes in, what you need to do is to drop the last bucket if its end time is out of the window size, because it's not useful. But if its end time is still within the time window size, you cannot discard it. You still need to keep it. And the new coming bit is either 0 or 1, the 2 different cases. And you have different methods to do the updates. If the new bit is 0, well, you do not need to do any change. So remember that the bucket always start with a 1 and always maintain the information of 1s. So if a new bit is a 0, it does not affect your summary information. So you do not need to do any changes. But if the current bit is 1, you need to do the updates for your buckets. You need to create a new bucket of size 1 for just this bit, just for this bit. And end timestamp is a current time. So you have a new bucket, okay? And then next, you need to propagate this update to up levels. If there are now 3 buckets of size 1, you need to combine the oldest 2 into a bucket of size 2. So now this step guarantees that you always have at most 2 buckets of the same number of ones. But now you increase the number of buckets to the next level, right? So you need to guarantee that for the next level, the number of buckets is still at most 2. So if to the next level, if there are 3 buckets of size 2, you need to combine all these 2 into a bucket of size 4. So you need to do this until you reach to the largest buckets, and then the update is finished. So let's look at one example about how to do the update. And this is a current data stream still shown previously. And next, if you have a new value 1 comes, okay, so this is a new value. A 1 comes, what to do is that you need to create a new window for this 1, a new bucket for this 1. But if you create a new bucket, you can see that there are 3 buckets of containing only 1, right? So according to this algorithm, you can only maintain at most 2 buckets for the same number of ones. So you need to merge the older 2 into 2 ones. So you need to merge this one as a 2 bucket. So now you have only 1 bucket of size 1 and 2 buckets of size 2, a number of ones as 2. And now you have 2 buckets of size 2. So okay, that's fine. You do not need to do any updates anymore because all the updates have been finished. It satisfies the requirements of this algorithm. But next time, if you get another 1, if next time you get 1, 1, and 1, 0, and 1, 1. So for this one, you just need to create a new bucket. So that's all. So you have 2 buckets with size 1, and the update is finished. And have a 0, nothing needs to be changed. And you have another 1, okay. So you see this step. That's a little bit tricky. And this new 1 makes you that you need to create a bucket for this 1. And you have 3 buckets of size 1. Well, because there's 3 buckets of size 1, you need to merge these 2, right? So you need to merge the 2 as a new bucket of size 2. But now you check for the buckets containing 2 ones. There are 3 such buckets. So in order to guarantee that at most 2 buckets containing the same number of ones, so you need to merge the oldest 2. So these 2 will be merged as 4 buckets. But if it is merged as a 4 bucket, then there are 3 buckets of size 4. So you also need to merge these 2 together as an 8 bucket. So this is merged as an 8 bucket. But there will be 3 8 buckets. So you need to update to merge the 2 older 8 buckets as a 16 bucket as well. And then you have 2 16 buckets. So you can see 1 bit may cause several update steps. This update means that you always need to guarantee the following things. First, either 1 or 2 buckets with the same power of 2 number of ones. You always need to guarantee this at most 2, either 1 or 2. And next, no buckets are overlapped. And next is buckets are sorted by size. So your update aims to maintain the properties. So this is the detailed steps of how to apply this algorithm to maintain a summary information for the data stream. And next is that how to do the query, right? Now we have the buckets, we have the information. How we can use these buckets to answer the number of ones questions? Well, to estimate the number of ones in the most recent n bits, you need to sum the size of all buckets, but except the last one. No, the size means the number of ones in the bucket, okay? And then for the last one, you add half the size of the last bucket. So the last one is unknown part. So you just add half the size of the last bucket into your answer. So remember that we do not know how many ones of the last bucket, right? So they're still within the wanted window. So we just add half the size of the last bucket. So for doing the query, for this example, if we want to know how many ones are within the n brackets, so we do 1 plus 1 plus 2 plus 4 plus 4 plus 8 plus 8 plus half of 16, that is 8. And we sum them together. So this is answer, approximate answer to the number of ones within the n bits. And the error bound is 50%. So as indicated before, this algorithm has small cost, space cost, and has performance bound. And why it is 50%? So suppose that the last bracket has size 2 power of r, so the last bracket, okay? Then by assuming 2 power of r minus 1 of its ones are still within the window. So we make an error of at most this value. And since there is at least one bucket of each of its size less than 2 power of r, so the true sum is this value. It's 1 plus 2 plus 4 plus 2 to the power of r minus 1 is 2 power of r minus 1. Okay, so this is the value that we are for sure. Okay, because at least one bucket of each of the sizes less than 2 power of r are maintained in your algorithm. Okay, so the true sum is always larger than this value, right? And this is at least larger than this value. This is error at most we make. So at most we make this error. So this one divided by this, we can see the error is at most 50%. At most 50%. So that's why we have error performance. Why the region does not work? So remember what we do before. The first solution is to maintain the regions. Okay, the region only store the number of bits, not the number of ones. So as a result, because the number of bits, so we are not sure how many ones are in the this region. So as a result, we cannot apply this proof to the region-based solution. But for the bracket-based solution, the bracket maintains the number of ones. So this is we know that at most the error is like this, and at least the final result is like this. So the error is at most 50%. We can guarantee a performance bound for this solution. And as in this example, so the largest one is 16 ones, right? But we have at least one bucket of size 1, one bucket of size 2, one bucket of size 4, one bucket of size 8. So we know at least 16 ones are contained in the final sum. And the error at most we make is always just 16. So it's that it's half. It's at most 8. So so the error is at most 50%. You can further reduce the error actually. So that means that instead of maintaining 1 or 2 each size bucket, you can allow either r minus 1 or r buckets, where r is larger than 2. So you have more buckets, and as a result, your space cost will be larger. And so except for the larger size buckets, you can have any number between 1r of those. And error is at most 1 or r. So if you select r to a very large value, so it means that error bound is very, very small. You can achieve a precision you can achieve the result to any precision. And by picking r appropriately, so you can trade off between the number of bits you store and error. So it's a trade-off between space and the error. So if you want to guarantee small space cost, but error will be large. So the current space cost, we have 50% error. But if you increase the space cost, then you can have smaller error. So that's a trade-off. Okay, so let's overview the algorithm again. Okay, maybe, I'm not sure if I explained too fast. So let's go back to the algorithm again and look at the problem again to see if you can totally understand. So the tech topic is about querying the data streams. And the querying data stream in this example we show is that we want to count the number of ones within the most unrecent bits. So that's a question we want to answer. Okay, so this is an example of the window size, and that's we want to do. So one easy solution is to store all the most recent bits, but because n may be very huge, and this is not practical, so we need to find another solution to solve this problem, right? Because we are not able to enter the entire window. And so there's one very naive solution to assume uniformly distribution. And so based on the historical distribution, we do an estimation of the number of ones. But normally the distribution is not uniform. So we need to find another way. And this is a DGM algorithm. And for the DGM algorithm, the advantage is that it has a small space cost, and it has performance bound, and it does not assume uniformity. And why it can achieve this is because it utilizes exponentially increasing buckets. Okay, so this first solution is just for explaining the intuition of this algorithm. It does not quite work. And by using the exponentially increasing regions, okay, so we are able to store the summary for the data stream. And by using these regions, we can answer the question approximately. But the problem is that we are storing the regions which covering the number of bits. So this does not have error bound, okay? And in order to achieve the performance bound, and we use a new method, and we use the buckets, not regions. So each bucket stores some bits, and these bits contain some number of ones. And this number of ones contained in each bucket increase exponentially. So that's the difference between the naive solution. And by doing this, for one data stream, we can use several buckets to represent the information for the data stream. And this shows an example. We have several buckets of some number of ones. And by representing the data stream as buckets, we are able to answer the questions approximately. So we sum up all the fixed parts to all these parts. We know exactly how many ones from here to here. And for unknown parts, and we only know that there is some number of ones in that bucket. And for that bucket, some ones are in the window, some ones are not in the window. And we only add half of the ones in that bucket to the final solution. And according to the analysis, this question is approximate answer can have at most 50% error. And so that's for the query processing. And next is about how you can maintain the buckets when some new bits come to our system, how to do the update. And the update is like this. About space cost, remember that log n for the time step to represent its end. Its end will be utilized to check whether a bucket is out of the current window. If it is out of the current window, so we can discard it. And another is to store the number of ones in this bucket. But the number of ones in this bucket is O log n space cost, because we only store, we make the number of ones is power of 2. Okay, so that's why it's log n. You can think about why it's like that. And for representing the stream by buckets, so we have several criteria. So we must guarantee that the right end of a bucket is always a position with a 1, and every position with a 1 is in some bucket. So for the same number of ones, at most 2 buckets have the same number of same number of ones. And the buckets never overlap, and buckets are sorted by size. So the earlier buckets are always no smaller than the later buckets. And so by with the given properties, so the updates is process is like this. Given you a new 0, you do nothing because this does not affect your existing buckets. And giving you a 1, you need to do the update. And updates is like this. So you create a new bucket for the size 1. And then you check for each level to see if the number of buckets is larger than 2. If it is not, you just stop the updates. If it is not, if it is larger than, there are more than 2 buckets, there are 3 buckets, you need to merge, you need to combine the oldest 2 buckets into a larger bucket. Then you move to the next level until you reach the highest level to reflect the updates. So this shows an example. I will show you the example again. Okay, you see the updates one step by one step. And this is an original data stream, and you have one. You create a bucket to store this 1. But now there are 3 buckets with 1. So you merge the 2, combine the 2 as 2 buckets. Okay, and now for the buckets with 2 1s, there are only 2. Okay, that's all. Stop the updates. That's finished. And next, if you have 1, 0, 1, the step is like this. You have another new 1. So 2 buckets with size 1. That's all. The update is finished. And 0 does not affect, so no updates. And another 1. So this causes some more updates. This one, you have 1 new bucket, but 3 buckets with 1. So you need to merge the 2 as 2 buckets, as a bucket containing 2 1s. But there will be 3 buckets containing 2 1s. You need to merge these 2. But if you merge these 2, there will be 3 buckets with 4 1s. So you always need to combine the oldest 2 4 buckets into 8 buckets. And 3 8 buckets, so you have to combine the 2 as well to 16 buckets. Then you finish the update. You always need to remember to check if the oldest bucket is, whether it is out of the window range. If it is, you need to discard the discard the bucket. Okay. And okay, so that's all. For this algorithm, what you need to store is buckets. And for each bucket, you have a timestamp and you have the number of 1s. So that's all. And the buckets are sorted according to their size, based on the time stamp. And for query processing, you first sum up all the known of all the for sure values. And for the unknown part, you add half of the value into your result. And this guarantee of at most 50% error. Okay. This is about how to improve the algorithm. So we can further reduce error to any precision, just by increasing the space cost. And extension is that the question about how many 1s in the last k within the most recent n bits. Well, it's just a modification of the DGIM algorithm. So you'll find earliest bucket B that overlap with k here. If k is here, so you find this bucket. And then the number of 1s is a sum of the sizes of more recent buckets plus half of the size of this bucket. So that's all. It's a very straightforward modification. If the stream is not bits but integers, and if you still want the sum of the last k elements, so you can do, you can still do some modification to solve this problem. So you can think about if you can solve this question. Well, in summary, well, we have summary here. For the summary of this algorithm, so we utilize exponentially increasing windows, and then you can do some extensions to solve more complicated algorithms. Okay, so have a short break, then we move to the next topic about filtering data streams. Okay, so let's finish the last two topics. Part 3 is to do filtering, about data streams filtering. So let's look at what this problem is about. And so in this problem, each element of data stream is a tuple, okay? And given a list of keys S, we want to determine which tuples of stream are in S. So obvious solution is to utilize hash table. And suppose that we do not have enough memory to store all of the S in a hash table. So we need to, for example, we might need to process millions of filters on the same stream. Well, because we are not able to store all of S, so as a result, we need to think about some smart ways to do this filtering. If we are able to store all of S, then it should be easier, right? So you can utilize hash table and to compute the hash values for the given tuples and to check if it is contained in the given set S. This application one example of this application is email spam filtering. For example, we know 1 billion good email addresses, whitelist. Okay, so if an email comes from one of these, so it is not spam. So we maintain a whitelist of emails, and we utilize this whitelist to check the email spam. It means that you are given some email addresses. It's a 1 billion good email addresses. Okay, and given them data stream, a lot of emails, your task is to check whether it is contained in the good email addresses, whether it is contained in this 1 billion elements. So because we are not able to store the 1 billion tuples, right? So it's different from the traditional method. So traditionally, if we can just do a search within the 1 billion elements or tuples if we are able to store them. And then if we can find the answer, then so we know it is contained. And if we are not able to find the answer, so we know it is not contained. So that's very easy. But because it's too large, we are not able to hold such a big given whitelist in memory. And how we can solve this problem. So that's the question we need to study. And applications we can also find such applications in publish subscribe systems. In such systems, you submit your subscriptions to the system, right? You subscribe some topics, and the system will publish the relevant results or messages to you. It will check whether each message match a user's interest, match the user's subscriptions. And if it matches, then the system will publish this message to the user. If not, then it will discard this message. So all these applications is relevant to this data stream filtering problem. So the first class solution is like this. Given a set of keys S that we want to filter, and we can do like this. We can create a bit array B of n bits. So initially it's all zeros. Then we choose the hash value H with range 0 to n. And next, for each member of S in this given key set, so we do a hashing. We hash them to this n bar case. And based on the hash values, so we set the relevant bit to 1. So this bit represents that, okay, so we know that there is one member in the given set, and its hash value corresponds to my bit. So that's a 1, the meaning of this 1. So it means that you compute the hash value for this element S, then you set the corresponding bit to 1. And next, for the data stream, for each element in the data stream, and we also compute its hash value. And if the hash value of this element in the stream the corresponding bit is 1 as well. Okay, so we guess this element A is in S because this A has one hash value, the same as the hash value of one element in S. So the probability that A is in S should be high. And we just make a guess, actually. And it works like this. Okay, so for the given S, we have a bit array. So this bit array is computed based on the given key set S. And the number of the value 1 represents that for this bit, okay, there is one element in S such that its hash value hash value corresponds to my bit. So that's for the bit array. And for the item, okay, so given one item, and the filter will first compute the hash value for the same hash value for this item, and then to check the corresponding bit to see if the corresponding bit is 1 or 0. And if it is 1, so we output this item because it may be in S. If it is 0, so we know that it cannot be S, right? If it is 0, means that it has the hash value of this element is not same with any. Is not same with the hash values of any element in S. So definitely this element is not in S. But if the corresponding bit is 1, so it means that the hash value of this element is the same as the hash value of some element in S. So possibly this item may be in S. So that's a difference for 0 or 1, the corresponding bit. And so actually this process creates false positives. False positive means that this element actually is not in S, but you report it as in S. That's called false positive. But it never creates false negatives. False negative means that this element is not in S. It's in S, but you report it as not in S. So this solution is also very simple, right? So there's some analysis based on, assume that you have 1 billion email addresses. And for this 1 billion email addresses, we use 1 gigabyte as a bit array. So we have 8 billion bits. And now if the email address is in S, so it is surely hashed to a bucket that has a big set 1. So there's no false negatives. And it means that if some email address is in, if given the data stream, given the email stream, if this email address is in S, then we will always report it as an answer. We can always find it. We will never miss such email address. So there's no false negatives. Okay. And approximately 1/8 of the bits are set to 1 because of this, because the data given to you, approximately, okay. And so about 1/8 of the addresses not in S get through to the output. So about this is the false positives. So some results actually they are not in S, but you report it as in S. But actually they are less than 1/8 because more than one address might hash to the same bit. Okay, but because remember the problem we are trying to solve is to filter out the spam email address. Okay, the majority of the emails are spam. So by doing this filtering, we are able to eliminate 7/8 of the whole spam. Okay, so that's kind of acceptable result, right? It's kind of still a significant benefit. We eliminate most of the spams based on these bit arrays hash functions. And there's some more analysis of this simple approach, and as a more accurate analysis for the number of false positives. It's kind of the zeroing dots, actually. So we are throwing m darts into n equally likely targets. So what is the probability that the target gets at least one dart? And in our case, the target is just a bar case, and the darts are the hash values of items. And we compute the hash values for the items. Then we set the corresponding bits to ones. And in so correspondingly, we can view the bar case as the targets and hash values of items as darts. We are throwing the darts to targets. And what is the probability that the target gets at least one dart? So what is the probability that one bit gets at least one hash value? So the one bit is set to 1. What is the probability that one bit is set to 1? So that's what we want to compute. And we have m darts and n targets, right? So what is the probability that the target gets at least one dart? And let's look at this analysis step by step. The first is the probability that some target X not hit by a dart. So some target is hit by a dart is a probability 1 over n. So some targets get hit. And it's a probability of 1 over n, and not hit by a dart is 1 minus this probability, right? And we have n, and this is a probability that at least one dart hits target X. We have m darts, right? So m darts not hit a target, not hit target, is this probability to the power of m, and the probability at least one dart hits target X, we use 1 minus this probability. And equivalently, n is sorry. So m can be computed as n times m divided by n, right? So okay, so this part is equals to 1 over e when n approaches to infinity. So finally, the probability is 1 minus e to the power of m divided by n. So that's our final probability. M is the number of darts, n is the targets. And in our problem, so the targets is the bits, and the darts are the hash values. Okay, so this is the conclusion. Now go back to our problem. So what is the probability of one bit gets value 1? The probability is fraction of ones in the array B is a probability of false positive. It's exactly of this probability, 1 minus e to the power of minus m divided by n. So given you 10 to the power 9 darts, and so in our example, it's 1 billion email address and 1 gigabyte bit array, 8 billion bits. So in our problem, the fraction of false positive by doing this computation is this value. Actually, it's smaller than 1/8, slightly smaller than 1/8, because some hash values will hash to the same bits, so that's why this value is smaller. Okay, so this is just a first naive solution. What we need to do is that because S is so large, we are not able to store S into memory. And as a result, we use a bit array to represent S by utilizing hash values. We store the hash values for S. So for each element in S, we use a hash value to compute a hash function to compute the hash value for the elements. And then based on the hash value, we set the corresponding bit in the bit array as 1. And so this represents that, okay, so this given use S, I have this bit array. And this bit array stores all the hash values of the given set. And next, in the data stream, you want to check if one element is contained in S. But what we have is only hash values of S. So we can only compare the hash value of the given data element with hash values of the elements in S. So we apply the same hash function to the element, to this element. And then we check if the corresponding bit in the bit array is 1 or 0. If it is 0, so we know that this element is not in S, definitely. But if it is 1, we know that it is in S, but not for sure. And there's some errors. And what is the probability of the error? So that's this value. So this probability of false positive. With this probability, and you may you may output a wrong result. So it is not in S, but you report it as a result. But anyway, you still throw a lot of, you still filter out the elements not in S correctly. Okay, so based on this simple solution, we have we can design a Bloom filter. So we use more than one hash functions. So previous solution we have only one hash function, and the only one hash function can get the probability of false positive to this value. And in order to improve the result, we want to decrease the probability of false positive. We want to make the result as accurate as possible, so we design the Bloom filter approach. The Bloom filter approach is that we use k-independent hash functions rather than only one. So the initialization is like this. We still use a bit array. And we hash each element as using all the hash functions. And we will set, for each hash function, for each hash value, we will set the corresponding bit to 1. And in runtime, because we have several hash functions, okay, we given an element in the data stream, we also apply all the hash functions to this element, and we get k hash values. And then we check if all the k hash values, the corresponding bits of these k hash values are of value 1. If all of them are 1, so we declare that x is in the given set S. And if not all the bits are 1, so we report that, okay, so this x is not in the given set S. Still, we will never create false negatives, right? Because if for all the bits, not all the bits have value 1, it means that for some hash function, okay, so this element has a different hash value with all the elements in S. So definitely this element is not in S. But if for all the bits, the values are 1, it just means that for these hash functions, that this element has exactly the same hash values with some elements in the given set S. But it still doesn't mean that this element is in S. So we use small hash functions, just increase the probability that this element is in S, but we can still not guarantee that it is definitely in S. So let's look at one example. Assume that we have a Bloom filter of size 10, and we use 3 hash functions. Okay, we have a bit array of 10 bits, and each x denotes the result of the 3 hash functions. Okay, assume that the for the first element x0, okay, the 3 hash values of the x0 is 1, 4, 9. So we set bit 1, 4, and 9 to 1, because it's the hash values we compute is like this, And for the next element x1 in S, we have 4, 5, 8 of the based on the 3 hash functions. So we set 4, 5, 8, 4, 5, 8 to 1s. So you can see 4, 4. 2 elements have the on one hash function, two elements are mapped to the same bit for different hash functions. Now, if you have a query y0, you want to check if y0 is in the given data set containing x0 and x1. So what you need to do is that you first apply 3 hash functions to y0, and you get the hash values 0, 4, 8. And then you go back to the bit array, you check 0, 4, and 8. So 4 and 8 are value 1, but 0 is not value 1. So you can declare that by 0 is not in the given set S. But if given your query by 1 with hash values 158, so you can see 158 or 1s. So based on this algorithm, actually you declare that y1 is in the given set containing x1, x0. But actually y1 may not be x0 or x1. So y1 actually is not contained in the given set. So this is a false positive. And you can see one example of this slides. Okay, sorry. Let's click this. So this example is more easy to understand. So you can see we have 15 bits, right? And you can create your Bloom filter here. You can provide maybe 3 strings str. So they will apply 2 hash functions to str and set corresponding bit. So 9 and 12 are set to 1. Okay, so there's one element. So you provide another one, ABC. So there's another element. Okay, so in this, now the bit array has 4 bits set to 1, right? We provide more FFF. So you get another bit. So this is a bit array. And your given set is str, ABC, and FFF, right? And you can check if a given element is, if it is in the given data set. So if you use str, so definitely it is in the data stream. And is element in the set? Maybe. The answer may be because the 2 hash values is 12 and 9. And 12 and 9, 9 and 12 are value 1s. So it will declare to be maybe. But if you use another one, AAA, it's 9 and 14, right? Because 9 is 1, but 14 is not. So it can note that this Bloom filter knows that AAA is definitely not in the given data set. So this is false negative, but Bloom filter never reports false negative. So let's look at if we can find a false positive, means which is not in these 3 strings, but the Bloom filter will report maybe. Okay, A, you can see A is not in str, ABC, or FFF, but its hash values 10 and 4 is 4 and 10. So these 2 bits are 1. So based on the Bloom filter, so the conclusion is maybe. It cannot be sure. But actually, this is a false positive because A actually is not in the given set. So that's more concrete example about Bloom filter. By using the Bloom filter, you apply more hash functions, and these hash functions help to decrease the false positive probability, and therefore the performance of the filter is better. And this is a more formal analysis of the Bloom filter based on the previous analysis. So what fraction of the bit vector B are 1s? So you are throwing k times m dots at n targets, right? Because now you have k hash values, hash functions, sorry. So the fraction of 1s is actually this value. And we have k independent hash functions, and we only let element x through if all k hash element x to a bucket of value 1. So only all the, it pass all the hash functions, then we can report this. So the false positive probability, we also need to get the power of k. And as a result, and based on this equation, we can do some computation. So for example, still given 1 billion and 1 billion email address, good email address, and 8 billion bits for the bit array. We use one hash function. This is a original value, what we have computed before. if we use 2 hash functions, we can see that the false positive has been decreased to about 5%, which is much better than the 12%. But it does not mean that we always need to use a larger k, because if we increase the value k, and the probability of false positive increase as well. So the smallest value achieves around 6, according to this equation. And you can, based on this equation, you can compute optimal k for the smallest positive, false positive probability. So in our example, roughly it is 6, and we can achieve about 2% for the false positive probability. Okay. The Bloom filters guarantee that no false negatives and use limited memory. It's about the bit array. It depends on how much size you give to the bit array. And it's great for preprocessing before more expensive checks. And suitable for hardware implementation, because hash function computations can be parallelized. Right? You can compute hash functions in different computers. And so it's better to have one big bit array or k small bit arrays. So actually it is the same, because based on the computation, the probability is the same. But if we just keep one big bit array, it's much simpler. So that's normally what we do. Okay. So that's for the Bloom filter. In summary, the Bloom filter aims to utilize hash functions to check, to filter if a given element is within the given data set. And the naive solution just utilizes one hash function. Okay, it applies this hash function to all the elements in the given set S, and then sets the corresponding bits in the bit array to ones. And the next given a data stream, it will apply the same hash function to this data element, and get the hash value, and then check in the bit array to see if the corresponding bit is 1. If so, it declares maybe. Okay, it may be in S, and if it is 0, so definitely it is not contained S. It can report a no. So always no false negatives, but possibly false positives. Means that possibly this element is not in S, but the Bloom filter reported it is in S. So in order to improve the performance, in order to decrease to reduce the false positive probability, and the Bloom filter tries to utilize more than one hash functions, use more hash functions to achieve better performance. The more hash functions means that for all the values, for all the elements in the given set S, you apply these hash functions to them and to compute the hash values and set corresponding bit to 1 in the bit array. And then given a data stream, you apply the same set of hash functions to get k hash values. And for the k hash values, and you go to the bit array to check if all the corresponding bits are 1s. If not all the corresponding bits are 1, so you can report no, because this element is definitely not in the given set S. But if all the bits are 1, so you can report maybe, because it may be false positive. But because you use more hash functions, and the probability of the false positive may be very small. So in our example, 1 billion email address, 8 billion bits. If you use 6 hash functions, the false positive probability is only 2%. Actually, about 98% of the whole data element of the elements in the data stream are reported correctly. So you can see this is very good results. Okay, for the last part is about counting data streams, and we utilize Sketch to solve this problem. And about Sketch, there's a lot of research to design Sketch for different problems. And this is a very important concept and also very difficult to understand. So in our lecture, I only briefly introduce the idea, not the details. And also we use only one problem to explain the sketch. Actually, there are different sketches for different problems. And in this part, I use the counting distinct elements as an example to show the ideal sketch. The problem is that given your data stream consists of a universe of elements chosen from a set of size n, And your task is to maintain a count of the number of distinct elements seen so far. So for example, the data stream is like this, 32, 5, 32, and 7. So you see these data streams, and the number of distinct values is only 5. So this value 5 is what you want to get. Okay, and if you are able to maintain all the elements seen so far, so this is very easy, right? So you can just keep hash table of all distinct elements seen so far. Then based on these results, you can easily return the number of distinct elements. So it's very, very simple. Again, the problem is that in most applications, it's not able to store the entire data stream you have seen so far. You can only have limited memories to store the summary of the data stream. So in this problem, we still need to think about what kind of information, what kind of summary information we can store to answer this distinct value question. There are a lot of applications for this problem, such as how many different words are found among the web pages being crawled at the site, or how many different web pages does each customer request in a week, and how many distinct products have we sold in the last week. So all these are used for some to get some statistics of the data, of the streaming data. And because we assume that we are not able to maintain all the elements we have seen so far, so we try to estimate the count in an unbiased way. We accept that the count may have a little error, so we can accept that the answer is not accurate, it's not exact, it's approximate, it's fine. But anyway, the answer should be limited, the error should be limited. There should be a performance bound, so that's our goal. In most of the data stream applications, we are only able to provide approximate answers, not exact answers. But we need to provide the performance bound to provide error bound. So you can also think about the fixed size fixed size sampling, about the filtering data streams, about the querying the data streams. We always have an error bound. And similarly, in this problem, we also need to do the same. For the sketches, sampling does not work because if a large fraction of items are sampled, so you don't know if they are all the same or different. So sampling cannot be applied in this problem. The sketch, the sketch is a technique takes advantage that the algorithm can see all the data, even if it can't remember it all. So it cannot remember all of them, but it can see all the data. And you can view it as a linear transform of the input. And a model streams as defining a vector. And the sketch is a result of multiplying the stream vector by matrix to obtain a result. And this result is called sketch and will be utilized to to answer the queries. And the algorithm we are introduced today is called FM sketch. It's proposed by two people in 1985, about 30 years ago. And this sketch has been used widely in many problems for distinct counting. It picks a hash value h and maps each of the n elements to at least log n bits. So for each stream element A, we use RA bit number of trillion zeros in HA. So first we apply a hash function. Okay, this hash function will map each of the elements to at least log n bits. And in the hash value of A, we use RA to denote the number of trillion zeros. So RA is a position of the first one counting from the right. So for example, if HA is 12, so 12 is 1100 in binary format. So RA is 2, the position of this one. And we record R as a maximum RA we have seen so far. So R is equal to the max maximum RV we have seen so far over all the items A we have seen. So roughly, we can do the estimation as the distinct elements can be estimated as 2 to the power of R. So that's a very rough estimation. Why it is like that? So let's look at some intuition of this algorithm. It's a very, very rough and heuristic intuition why this FM sketch works. So HA, the hash value, hashes A with equal probability to any of n values, right? So this is about hash function. And HA is a sequence of log n bits where 2 power of minus R fraction of all A's have a trail of R zeros. So what does this mean? So all the elements, so think about given all the elements, about half have a tail of only 1 0, right? So only 1 0 means that his hash value is even number, right? And if it is 1, it is odd number. And so about half of all the hash values of all elements have only 1 0, right? Then for odd elements, about 25% have 2 tailing zeros, right? So it means that the hash value of that element actually can be divided by 4. So that's why it's about half, 1/4 of the elements have a tail of 2 zeros. So similarly, about 1/8 of all elements have hash values of a tail of 3 zeros, right? Because that is, the hash value of the elements can be divided by 8. So it has 3 tailing zeros. So that's what does this mean? So if all elements have a tail of R zeros, so about R to the power of minus 2 to the power of minus R fraction of elements have a tail of R zeros. So that's the idea of this of the intuition of this algorithm. So about 50% of the odd elements hash to some values has only 1 tailing zero, and about 25% of odd elements hash to 2 tailing zeros, right? So if we saw the longest tail of R is 2. So the atom hash adding the hash value of the items and with 2 tailing zeros. Then probably we have seen about 4 distinct elements so far. So that's the basic idea. So it takes to hash about 2 to the power of R items before we see 1 with 0 suffix or less of R. So that's why we can use 2 to the power of R to estimate, roughly estimate the distinct elements, just because of this observation about the tailing zeros. The percentage of the elements has to different number of tailing zeros. I'm not sure if I made this clear because it's not very straightforward to understand. And so let's go back again to about the steps. And we use one hash function. This hash function applied to all the elements, okay? And for all the elements, for each hash value, we will compute RA, which is the position of the first one, counting from the right to the left for the hash value of each element. And then we will get the maximum RA we have seen so far. So that is leftmost position of 1 for all the hash values of all the elements in the data set. And then we use 2 to the power of R to estimate the distinct elements. So the reason is because of this, because about 15% of the elements are hashed to 1 tailing zero, and about 25% hashed to 2 tilde zeros, and 1/8 of the elements are hashed to 3 tilde zeros, right? So if we see R as to the maximum R, the longest tail is only 2, so we only have 2 tilde zeros at most, based on all the observations. So it means that the distinct items is roughly about only 4. Because if it is larger, then we should be able to see more tilde zeros, not just 4. And more formally, it's like this. So we can show that the probability of finding a tail of R0 is like this. It goes to 1 if, so M is the number of distinct elements we have seen so far in the stream. So if we have seen M distinct elements in the data stream, if the number of M is much larger than the value of 2 to the power of R, so the probability of finding a tail of R0s should be very close to 1. The reason is because M is much larger than 2 to the power of R. So as a result, the value is very large. So we are able to find the tail of R0s because R is relatively small compared to M. But in another hand, if M is much smaller than 2 to the power of R than this value, well, the probability of finding a tail of R0s will be very small. It's approaches to 0 because we are not able to see so many distinct elements. Therefore, the 2 to the power of R is just a round M. It's a very rough estimation of the number of distinct elements. And we can use more formal analysis like this. So the probability that a given HA ends in at least R0s this value is 2 to the power of minus R. It means that so for given element A, and we have a hash function H. So HA applied to A can hash the elements uniformly at random to the range from 0 to n. Then the probability that a random number ends in at least R0s is 2 to the power of minus R. It's still based on the previous observation, because about 50% of the elements can be hashed to a value with only 1 tilde zero, and 25% can be hashed to values with 2 tilde zeros. And as a result, the probability of not seeing a tail of less R among elements is like this: is 1 minus 2 to the power of minus R and to the power of m. So this is a probability not seeing a tail of less R, and this is a probability of among m elements. So finally, this probability computes all n in fewer than R zeros. I'm sorry that this part is a little bit not straightforward and some mathematics are involved. So I recommend that you read the textbook, so more details are shown to you, so you can have more time to think about the whole procedure. And if you cannot follow, so you just need to remember the conclusion. Okay, the conclusion is that, after some computation, the probability of not finding a tail of length R is, if m is very much smaller than 2 to the power of R, so the probability tends to be 1. And so the probability of finding a tail of length R tends to be 0. But on the contrary, if m is much larger than 2 to the power of R, so the probability tends to be 0. And this is because of this. And so based on this equation, this is just a formal analysis of the conclusion before about this conclusion, about the conclusion here. So this about explanation of why we can use 2 to the power of r to estimate the distinct number of m. It's always around this value m. So we can see a more concrete example. Okay, so it's about FM sketch. We still use a bitmap array of L, and where L is log n bits. So we initialize the bit array to all zeros. And for each incoming value A, we first compute the hash values. Okay, we first compute HA. From HA we get RA. RA is the position of the rightmost one. The first one we can find from right, counting from right to left. And then we set corresponding bit to 1. And for all the elements, we'll process like this. So for each incoming, after we process all the elements, if D distinct values, so we expect that about half of D mapped to FM1, and about 1/4 of D mapped to FM2. So this is a whole FM bitmap. And this is about the position where smaller than log D. And this is about the position larger than log D. So this is a rough part of the element, the number of distinct elements M. For all the value 1s and for all the value 0s, we know that they are for sure. M cannot be there, M cannot be there. The distinct number of M must be larger than these values and must be smaller than these values. But we are not sure where M is around this range. So in the paper, previously we used the leftmost one. So this just what we have seen before. It's a maximum RA we have seen. Then we use 2 to the power R to estimate M. But in fact, according to the original paper, there's very complicated analysis. You can not use this value because it's not accurate. So you can use this estimate D is equal to C to the power of R. For C is roughly 1.3 to do estimation. It's a more accurate estimation. And original paper is published in 1985, and you can, if you really want to know details, you can find this paper to read the detailed analysis about estimation. You can also use more than one hash functions to improve accuracy, just like the Bloom filter. Okay, so that's for the last part. And because the last part is a little bit complicated and also not easy to explain, so it is not required in the final exam, so don't worry about last part if you cannot understand this part. So no worry, not covered in the exam. I just help you to know that there's a kind of technique called sketch. So the sketch can help you to do some problems. And this is called FM sketch. And for some other sketches, such as Coulter-Mean sketch, AMS sketch, so these sketches can be utilized in different scenarios. So if you they are dealing with streaming data, and possibly these sketches may help you. When you meet some problems, you can try to see if the sketch technique can help you to solve the data stream problem. And for more details, you can refer to chapter 4 of Manual of Massive Datasets. So for some proofs and for some more details are shown in that chapter. And okay, so that's for today's lecture. And remember that the third project has been released. You have 2 weeks to do the third project on Spark. So next week is a recess week, right? So we have no lectures, right? Okay, so see you 2 weeks later.
Can I ask you the tutor's name? So can you know him?
I think you can find in the first lecture slides. I'll check. Oh, sorry.
Fabi.
Yeah,
So if I Google him,
Not sure. I'll try to see if I can find his email for you. Okay.
I think you can see on the timetable.
Timetable?
there he is.
Okay. Yeah, you can Google.
You
Maybe
can
you
get
stop.
him.
Yeah.
Okay.
Yeah.
I just want to ask him a couple questions.
Yeah. I think he can help.
Yeah, like how to access the counter.
What's the counter? In Python, right? Okay.
No,
Okay.
thank you.
Okay.
I just want to make sure that this part is not included.
Yeah, it's not
Just
included.
starting from the part 4, like
Yeah.
all the
Yeah.
the 16.
Yeah.
Okay. But 1, 2, 3 are.
What period? Yeah.
Thank you.
I guess the last part is not explained clearly, right?
Yeah, so it's a little bit fast, and also the theories are not too clear, and it's just some rough approximation about it.
Yeah, I know because detail. Actually, there are many details about this part, so it's hard
I
for
know
me
it's
to.
pretty much complicated if we.
Yeah,
dig too deep.
yeah. That's why it's not included in the exam. Okay.
Thank you.
Okay. Hi.
I'm trying to make Spark working. So I'm trying to remember command. What is this?
Which area? Text file.
Oh, I forgot to close.
Yeah, now you can do.
That's why. It's so easy to make like small mistakes.
Yeah, so you need to practice more.
Yeah.
Yeah.
Regarding project 3,
I think just this one will be chapter 6. And also the labs. The labs instructions are very important. So you see, actually in the lecture we didn't introduce too much about Spark programming, and more materials are provided in two labs. It's better to finish the Spark lab and then begin the project.
is there any particular labs?
You just this lab.
6?
Let me check that.
6 or 7? This one,
I think this one should be very.
yeah, this is the first introduction as well.
Okay, then should be very doesn't have more problems about the Spark programming and I give you some answers. And also the slides of chapter 6 is very short. Yeah. You will practice more in this week's lab actually. You will be given more Spark problems.